A single thunderstorm can unleash more energy than an atomic bomb, dramatically shaping our local environment. Imagine colossal rivers of air silently guiding entire weather systems across continents every single day. These invisible atmospheric currents dictate everything from a gentle spring breeze to devastating supercell storms. Understanding these powerful, intricate weather patterns reveals the true dynamic nature of our planet. Weather patterns represent the predictable, recurring atmospheric conditions that define specific regions globally. They profoundly influence agriculture, determining crop yields and food security for billions worldwide annually. Maritime shipping routes and aviation schedules critically depend on accurate forecasts of these dynamic patterns. From daily commutes to long-term infrastructure planning, weather deeply impacts human civilization's daily rhythm. These complex patterns arise primarily from the sun's uneven heating of Earth's surface and atmosphere. Tropical regions receive direct, intense solar radiation, creating warm, rising air masses continuously. Conversely, polar regions experience less direct sunlight, resulting in colder, denser air that steadily sinks. This fundamental temperature difference drives the initial large-scale atmospheric circulation across the globe.
Earth's rotation then spectacularly deflects these moving air masses, creating complex wind systems and currents.
Water, in its liquid and gaseous forms, acts as a massive energy reservoir, influencing countless atmospheric processes. Ocean currents also significantly contribute, distributing heat and moisture globally through vast, swirling gyres. Together, these interconnected forces orchestrate Earth's magnificent, ever-changing weather patterns we observe. The sun's energy absorption creates pressure differences, causing air to flow from high-pressure zones to low-pressure areas. This movement of air generates winds, ranging from gentle zephyrs to fierce hurricane-force gusts impacting coastlines. As warm, moist air rises, it cools and condenses, forming clouds that later release precipitation like rain or snow. Cold air fronts occur when a dense, cold air mass pushes beneath a warmer air mass, forcing it upwards rapidly. This rapid uplift often leads to dramatic weather events, including intense thunderstorms, hailstorms, and lightning. But that's not the strangest part about these atmospheric interactions, as something more subtle also occurs. Warm fronts form when a warm air mass gently glides over a cooler, denser air mass, gradually replacing it. This produces widespread, steady precipitation, often lasting for extended periods, like soft, persistent drizzle. Occluded fronts develop when a faster-moving cold front overtakes a slower warm front, lifting the warm air completely. These complex fronts combine elements of both, bringing varied weather conditions from heavy rain to lighter showers. Stationary fronts occur when two air masses meet but neither advances, leading to prolonged, unchanging weather. Imagine a colossal, invisible river of air, thousands of miles long, meandering high above the surface. The jet stream, these powerful, fast-moving currents of air, typically found at 30,000 feet, steer entire storm systems across continents. The polar jet stream, particularly impactful, separates cold Arctic air from warmer mid-latitude air masses. Its wavy path directly influences where major storm tracks develop, bringing significant weather changes to regions. Wait until you hear what comes next regarding how these global patterns connect to everyday forecasts. Ocean currents, like the Gulf Stream, transport vast amounts of heat from the equator towards the poles. This oceanic heat transfer significantly modifies regional climate and weather patterns, especially near coastal areas. El Niño and La Niña, specific oceanic phenomena, represent massive shifts in Pacific Ocean temperatures and currents. El Niño involves warmer-than-average Pacific waters, altering global rainfall patterns and causing widespread droughts or floods. La Niña, conversely, brings cooler-than-average Pacific waters, often intensifying hurricanes in the Atlantic basin. These cyclical events demonstrate how interconnected Earth's atmosphere and oceans truly are globally. High-pressure systems generally bring clear skies and stable weather, as air slowly descends and warms. Low-pressure systems typically create cloudy, unsettled conditions because air rises, cools, and forms precipitation. The rotation of these pressure systems, clockwise in the northern hemisphere and counterclockwise in the southern, is crucial. This fundamental Coriolis effect deflects moving air and water, creating predictable spiral patterns in storms. Hurricanes, for example, are gigantic low-pressure systems fueled by warm ocean water and immense latent heat release. They represent the most powerful storms on Earth, capable of catastrophic winds and devastating storm surges. Tornadoes, conversely, form from supercell thunderstorms, creating violently rotating columns of air descending to the ground. And then something unexpected happened in our understanding of how these smaller events are triggered. Scientists constantly monitor these intricate interactions using satellites, radar, and ground-based observation stations. Accurate weather pattern forecasting saves countless lives by providing early warnings for extreme events like floods. Communities can prepare for approaching blizzards, heat waves, or severe droughts, mitigating potential human suffering. Farmers rely on these predictions to decide planting times, irrigation needs, and harvest schedules, ensuring food supply, dictating plant growth cycles and animal migrations, anticipating demand spikes during hot or cold snaps. Transportation industries, from airlines to freight shipping, adjust operations based on expected weather disruptions. Major sporting events and outdoor festivals often reschedule or cancel due to adverse, unpredictable weather patterns. Weather patterns also profoundly influence natural ecosystems, dictating plant growth cycles and animal migrations. Prolonged droughts stress forests, increasing wildfire risks and impacting biodiversity across vast regions. Intense rainfall can trigger devastating landslides, altering landscapes and destroying critical habitats rapidly. Shifting seasonal patterns affect fishing industries, as marine life migrations respond to changing ocean temperatures. Global weather phenomena like monsoons are absolutely vital for agricultural productivity in many Asian nations. Understanding these patterns helps urban planners design resilient cities, capable of withstanding future extreme conditions. Scientists continually study historical weather data to identify long-term trends and anticipate future atmospheric shifts. This crucial research informs policy decisions regarding resource management, public safety, and environmental protection. Our collective future significantly depends upon a deeper, more comprehensive understanding of these dynamic forces. Every single day, weather patterns shape our world in profound and often surprising ways, demanding our attention. Ultimately, weather patterns are Earth's intricate, powerful circulatory system, constantly distributing energy and moisture. They remind us of our planet's immense power and the delicate balance within its atmospheric envelope. Daily, continued scientific exploration helps us better predict and adapt to these magnificent, relentless natural forces. Appreciating their complexity empowers us to live more harmoniously with our dynamic, ever-changing environment. If you found this journey through atmospheric science fascinating, hit subscribe for more incredible discoveries. Like this video to support our educational content, and share your thoughts in the comments below. Join our community as we continue exploring the astonishing science that shapes our world every moment.